channel. So today we will be covering the second part of module 3, which is circuit characterization and performance estimation. So circuit characterization and performance estimation means what are the characteristics in the circuits, and we take the help of R and C estimation for performance estimation, because basically T is equals to R into C. This is the basic delay formula. So as R and C, both R and C, as the value of R and C increases, or the number of resistors and capacitors increases, that is directly related to our delay. Okay. Therefore, we need to find out the resistance and we need to find out the capacitance associated with our circuits. Hence, we are covering this first, resistance estimation. So the resistance of a uniform slab of conducting material may be expressed as, this is the formula of resistance, where rho is the resistivity, T is the thickness, L is the length of the material, and W is width of the material. So basically we know resistance, it is directly proportional to length of the material, and it is inversely proportional to the area of the material. Okay, so that is what this formula is also indicating. Thickness into width is basically giving us the area, and here we have L. Okay, and if you remove this proportionality and if you put a equal to sign, there will be a constant coming, that is called as resistivity, right? And we can rewrite this expression in this form, where resistance is Rs into L by W. Okay, so what is Rs? Rs is nothing but rho by T. So we will be using this formula, which is very important for problems. Problems we will take in next video. Let me cover the theory part first. Next we have MOSFET as capacitor. So as we know, this is the gate. I can take the highlighter. So I am highlighting the yellow portion is the gate, okay, and the blue portion, it is the SiO2. That means it is an insulator, and again the yellow portion below the SiO2 is the channel. So both the yellow portions are acting like two plates of the capacitor, and blue portion, which is an insulator, it is acting like dielectric. So this is how every MOSFET acts like a capacitor. And again we have one more capacitor below it. Okay, so we have channel, this is represented in blue color, right? And we have one more depletion region that also acts like insulator. Why there is a depletion region? Because channel might be N and the substrate might be P. So if we have N channel and P substrate, there will be a PN junction, and between PN junction definitely there a depletion region is formed. Okay, so blue color is again uh, dielectric or insulating material, and we have again P substrate below it. So actually we have two capacitors, which I am indicating here on the left hand side with the purple color. So the first capacitor is Cg, okay, and the second capacitor is C depletion. So this is how every MOSFET will behave like a capacitor. So next we have a graph which is indicating uh, it is the capacitance CGB by C naught versus VGS. So for various values of VGS, right, how the capacitance varies. So in the very basic working of MOSFET, we have seen there will be an inversion region, okay, there will be a depletion region, and there will be accumulation of charges. So during the accumulation of charges, the capacitance will be maximum, and then the capacitance decreases. Okay, and we have formula for capacitor. C naught is equals to epsilon SiO2 into epsilon naught divided by TOX. So epsilon SiO2 is why we are taking epsilon SiO2, because SiO2 is the layer which we are using as oxide layer. Okay, and the dielectric constant or the relative permittivity of SiO2 is nothing but 3.9. The value of it is 3.9. And as I said, the capacitor acts like the MOSFET acts like capacitor. So here you can see there is a capacitance coming into picture. Okay, and we had seen only two capacitances in the previous slide, but here you can see there is a capacitance between source and body. There is a capacitance between gate and body. There is a capacitance between gate and drain, and capacitance between gate and source. Here we have capacitance between drain and body. Okay, so capacitance means what? If there is any depletion region or any dielectric or any insulator in between, and on either sides of the dielectric we have charges, then it naturally forms a capacitor. Okay, so here we have 5 different types of capacitors which we have not done anything, but they are a part of this MOSFET. So they are called as parasitic capacitors. And the total capacitance, it is Cg, which is the sum of CGB plus CGS plus CGD. Okay. Then we have a table. On the right hand side, you are seeing a table. 4 micrometer silicon gate CMOS process capacitances. So these are the values which are the capacitor values for gate polysilicon, metal ore poly, metal ore field. So these values will be very helpful for solving the problems. We'll take up when we go with the problems. And I was speaking about the parasitic capacitances, which looks like this. There is a MOSFET, and between any terminal of the MOSFETs, we will see that there will be capacitors formed. These are parasitic capacitors. And when we look at circuit as a whole, then we will see that there are number of resistors and number of capacitors, maybe series parallel in any combination, and we need to just try to calculate the performance. We need to measure the performance due to these R and C's, because as I said initially, T is nothing but time delay, which is directly proportional to R value and C value. Next we have switching characteristics. What is switching characteristics is whenever there will be any switch between there will be any switch between 0 and 1 or 1 and 0. Okay, that is called as switching. Say for example, here I have the first circuit is a NOT gate, left hand side, and the output of NOT gate is given to the second NOT gate. Output of first NOT gate is the input to the second NOT gate. So when I change my input from 0 to 1 or 1 to 0, the output will also change. Say input is changing from 0 to 1, okay, then output will change from 1 to 0, but that will not be a sudden change, though input will change like a straight. Okay, this is the input, say this is my input, but the output will not change suddenly because I have a capacitor which is called as capacitive load. So it will take time to charge and discharge. Hence you are seeing the blue color shaded output, which is telling us that the output is changing slowly. Okay, and this slow change actually introduces few terms. Those terms are called as rise time, fall time, and propagation delay. Okay, so what is rise time and what is fall time? Basically, say I am giving the input, for example, 0 volts to 10 volts. Okay, I am taking very simple example, 0 volts to 10 volts. So when I give input from 0 to 10 volts, the waveform will rise from 0 to 10 volts. When it is transiting from low to high, it will rise from 0 volts to 10 volts. Okay, so when it is rising, you can see the purple color mark here. So this purple color mark here, the signal is rising, the output signal is rising. Okay, so when it is rising from 0 to 10, okay, the time required by the signal to rise from 1 volt to 9 volts, time required by the signal to rise from 10% of the maximum value. So maximum value is 10, take the 10% of 10 will be 1. So from 1 volt to reach up to 90% of the 10 means it is 9 volts. So they have marked this line, you can see the red color. Okay, this is one red color which is 10%, and this is one red color, second one, which is 90%. So the signal is rising here from 10% to 90%. Okay, how much time it is taking to rise from 10% to 90%? That time itself is rise time. And the converse is fall time. So the signal is falling from 10 volts to 0 volts. Okay, then how much time it will take to reach 1 volt from 9 volts? So 90% to 10%. How much time it takes to fall? That is fall time. And here we have two formulas. This is rise time formula, fall time formula. Okay, this is the beta ratio. Actually, when beta ratio changes, yes, the rise time, fall time all changes. And here we have the general thing, WP. It should be 2 times of WM. Why it is? Width of PMOS is doubled. Why it is doubled? Because PMOS is having less speed compared to NMOS. Then we have average time. Average time is nothing but the TPLH plus TPHL divided by 2. Here they have denoted it with a different notation. So the average time or average delay, what it is nothing but the average of these two. Okay, average of these two. And we have something called as propagation delay also, PP, propagation delay. That delay is nothing but mark the input. So you can see the purple color which I am shading here. So this is input, where input is crossing 0 to 1, shifting from 0 to 1. Okay, and here is my output falling. So mark the 50% of the value, and here also mark the 50% of the value, and see the difference. See the difference. Say it is 1 second, and here it is say 2 second. Then 2 minus 1 second will be my propagation delay. Okay, So it is 50% difference of input and output waveforms in terms of time when they are crossing 50%. When they are crossing 50%, means input is say 5 volts at this point, 50% of 10, and output is 5 volts at this point, that is 50% of 10. So if so the time difference between input and output when they are at 50%, that is nothing but propagation delay. Okay, next is power consumption. So what is static power consumption? Static power consumption is nothing but uh, when the MOSFETs are off. When the MOSFETs are off, what is the leakage current that is flowing? Okay, that leakage current into the supply voltage is the static power consumption. Basically, what is power? Power is P is equals to I into V. So P is equals to I into V. So I is nothing but, you will say the current will not flow when the device is off. Yes, definitely the current will not flow when the device is off, but still there will be a reverse saturation current which is studied during diode. Okay, and you will say this is not a diode, but still we have something called as P substrate, okay, or P well, and here we have N, P and N. Okay, so between P and N, there it is acting like a diode. So actually MOSFET is completely different than diode, but MOSFET is a structure in which we can find PN junction. Okay, and this formula is the reverse saturation current of diode. I naught is equals to Is into e raised to qV divided by kT minus 1. Okay, the parameters are written here: voltage, diode voltage, charge, Boltzmann constant, and temperature. So whatever current is flowing, though it is very small and reverse direction, that current into supply voltage will be the static power consumption, and we know that this current is very small, therefore the static power consumption will also be very small. Okay, so whenever the device is off, say MOSFET, P MOSFET, N MOSFET is off here and the P MOSFET is off here, so we'll try to calculate what leakage current is flowing through that into VDD will give us static power consumption. Next is dynamic power consumption. So what is dynamic power consumption is, the dynamic power means whenever there is a switching between input and output, or whenever there is a switching, I mean to say the MOSFET is turning on from off state and the MOSFET is turning off from on state, that is called as switching. So during that on and off state switching, whatever current flows through the MOSFET, that current into the supply voltage will give us the dynamic power consumption. Okay, this is another formula, and the total power is nothing but summation of static power and dynamic power. So here you can see the VDD input. This is the input. It is falling from VDD to 0, and the output is shifting here from 0 to 1, right? And during this transition, there will be little current flowing through the MOSFET. That current into the VDD will give us the dynamic power. So dynamic power is very large compared to static power. Next is scaling of MOS transistor dimensions. So what is scaling is? Scaling is reduction in size, okay, reduction in length or reduction in width or reduction in these parameters, gate oxide thickness, reduction in supply voltage. Okay, so basically scaling means reduction. So reduction might be with respect to all these parameters which are listed here. So what is scaling? Scaling is reduction in reduction. Okay, scaling is basically reduction. So whenever we try to reduce the length or whenever we try to reduce the width or the other parameters, okay, they affect the performance. they will influence the performance. Some most of the time the performance increases, okay, as we go with smaller circuits or smaller dimensions. Most of the time the performance improves, okay. So the what is the scaling factor is? Scaling factor is, say, 1 by alpha. What is alpha? Alpha is a general term here, okay. So if I make alpha is equals to 2, then I can say that the length has been reduced to 1 by 2. That means the length is halved. If it is 1 nanometer, then we will go with the half nanometer, okay. Even the width and gate oxide thickness, all things, okay. And doping concentration or substrate doping, okay, that is, if all these are becoming 1 by half, then it is alpha, okay. It is 1 by alpha, then the substrate doping, it will become alpha. And power dissipation. So if what are these actually? If I reduce the length to 1 by 2, then the DC power dissipation, it will be becoming 1 by alpha to the power 2. Say if I am reducing the length to half, then my power dissipation will be becoming 1 by half raised to 2. That means 1 by 4 compared to previous power dissipation. Say for example, if my circuit was consuming 10 milliwatt earlier, then that 10 milliwatt will be reduced to 1 by alpha raised to 2 times, okay. So it will be consuming 2.5 watts milliwatts. It will be consuming 2.5 milliwatts. Because I am reducing the length by 2, the power will be reduced by 4. That is the meaning of this. DC power dissipation, it is decreasing, or it is changing 1 by alpha raised to 2. I hope you have understood this. Dynamic power also reduces with the same scaling factor. Okay. So if I change the length or width, these parameters changes accordingly. Next we have length versus voltage versus doping concentration graph. So this is the channel length which we are varying, okay, and this is the voltage, supply voltage, and this is the doping concentration graph. So this graph tells us that as the channel length decreases and as the supply voltage decreases, okay, the doping concentration also decreases. So it is an advantage. Like channel length decreases, supply voltage also decreases. All these things results in low power. Okay, and accordingly we should decrease the concentration also, doping concentration also. It should not become like I have a playground of 1,000 capacity, but 10,000 people are allowed to enter in that, okay, because the channel length is decreasing, okay, the voltage is decreasing. Accordingly, the number of charge carriers present in that should also be decreased. This is the graph which is giving us that idea. And next is yield. Yield is a term which is defined as number of good chips on wafer divided by total number of chips. Means this is the product. Say I had a silicon wafer. On that wafer I have manufactured or fabricated 100 chips. Out of 100 chips, how many chips are working perfectly? Say 50 chips are working perfectly and 50 chips are having error. Then my yield is, it is 1 by 2, or it is 50%. Okay, it is 50 by 100 into 100%. So yield is always represented in terms of percentage. It is 50 by 100 into 100%. That is 50% is my yield. So ideally yield should be uh, more to reduce the fabrication costs. And there is a model, seeds model, which gives us formula for yield. Okay, these are the parameters, area and defect density. Also Murphy's model is there, which gives us another formula to calculate the yield. But basically the meaning of yield is how many good number of chips have come out from total number of chips fabricated. Thank you.